In this PlayPosit video, you're going to practice determining whether or not an argument is valid or invalid. And of course, after you've given it your attempt, you will be shown how to go about figuring that out using truth tables. So for example 1, you're given this symbolic argument, which basically, if you read it more in English, would be if P then Q, if Q then R, therefore if P then R, which basically, when you're doing this kind of argument, you're assuming that anything above that bar is true, and if both of those are true, we're saying therefore if P then R has to be true as well. So here's how you could determine if it's a valid argument or not using a truth table. I'm going to set up the truth table with P, Q, and R, and these are all the possible combinations of true and false that these have. And I'm going to look at these two premises, these two given statements. And again, we want to assume these to be true. So I want to figure out where these will be true. So I'm going to look at both of those. And using the same methods we used before to come up with these truth tables, I'm looking at P and Q to figure out this one here. And basically, this will be true as long as either both P and Q are true or if P is false. So, same thing with Q and R here. So these are the truth tables you would get for these two statements. Now we want to see is if P then R is true for the cases where both of these are true. So I'm only going to look at to see where both of these are true, and these are the 4 instances where they're both true. I really don't care about these other ones. You're going to see I fill in the truth table for it, but I'm really focusing my attention on these. And if you want to save yourself some time, once you establish, whether or not your conditions are true or not, you can just focus on the ones where all those conditions are true. You might have 2, 3, even 4 statements up here. So it can save you a good bit of time if you just focus your attention only on the ones that both of those are true or all of them are true. We just want to see what happens in this instance. So I'm going to do if P then R. Same premise here. Either both P and R have to be true or P has to be false. And based off of that, looking at those two columns here, these are the values I get. So as you see here, you can see the true values of these, but I have them lightened a bit because they're not important to us. It's only the ones for these 4 rows that I'm concerned about. And as you can see, everywhere where both of these are true, if P then R is also true. Therefore, this is a valid argument. So, and basically this is the law, I forget which law, I want to say it's the law of syllogism off the top of my head. But, essentially, this is one of the laws that are brought up in the material that you have a look at. So this is basically the proof of that law. And each one of those laws that are listed can be proven in a very similar way. And as a matter of fact, you might see some exercises out of the textbook where that's in fact what they ask you to do. Now, moving on to the next one. If not P, then not R. So a lot of students get this, get situations like this mixed up, and they think that this is an automatic consequence. Basically, if P brings about Q and Q brings about R, if P doesn't happen, they think, well, Q's not going to happen, and therefore R is not going to happen. They just, without looking at a truth table, they think this is a valid argument. Well, let's have a look at this again. So I'm going to take some shortcuts because a lot of since these two premises are exactly the same as the previous one, I could just kind of cut to the chase and get to that point here. And again, I'm only going to focus my attention mainly on these 4 rows where both of these are true. But I do need some more information to figure out what goes on with this statement, if not P, then not R. So I got to get a column for not P, and I got to get a column for not R. And that's just basically me doing the opposite true values for each one of the things in P, and the same thing for R. And I want to see, okay, well, now looking at these 2 columns, and either both of these need to be true at the same time, or if this first one is false, it's automatically true. So based off of that, these are the values. Now, as you can see, There's instances where both of these are true, and that statement's true, and there's instances where both of these are true, and this final statement is false. It only takes one of these to happen, and because of that, these two falses that are here. This is not a valid argument. So this is not an automatic consequence of the two premises occurring. So that's why this is not a valid argument. On the other hand, if I reverse this a little bit and say, okay, if P happens and Q happens, if Q happens and R happens, then basically if R doesn't happen, that implies that P didn't happen. Is this a valid argument? This is actually an argument which is very similar to, well, it's not one of the laws directly. It's kind of very similar to a law of contraposition, but not entirely, because you have you have a secondary conditional statement here, but it's a very similar type thing. But as you can see, we're going to prove that this is in fact the case. So as I go through this, again, same truth table. I still have the same columns here. It's still these are still the two premises, same two premises we had in the previous one, so same truth table. Now if I look in this direction here, same two columns, but now this is the first one I look at. So it's either going to be where both of these are true, or when this one's false. This statement ends up being true, and as a result, this is what I get. As you see, there's other values for the truth values, and there's some truth values that this is false, but they don't occur when both of these are true at the same time. And that's the premise we're making. We're assuming that these two are happening and are true, and we want to see if this is true as a result. In every instance where both of those are true, this statement's true. So this is a valid argument as well. So keep in mind that, don't just automatically think that when you're doing this truth table, if you look at that last column for your final argument and you see that it contains a false value, that doesn't mean it's going to be an invalid argument. It's only going to be the case if that false is occurring when all of the preconditions, all the conditions that are put on initially are true. That's when that false is going to dictate that you have an invalid argument. And along with this, for this one here, it stands to reason, if you look back at this, if not R, then not P is the contrapositive of if P, then R. And we proved this one in the first part of this example. So it stands to reason if this is the contrapositive in the original conditional statement should have the same truth value. So as you can see here, that would be the same. And that's also a valid way of proving it. If you recognize, well, wait a second, if I've proven that if P then R works under these conditions, and I know that if not R then not P is the contrapositive of that, that's enough of to say, well, since this is the contrapositive, this would too be a valid argument as well. And that is a legitimate proof if you recognize it. And that is the end of this video. If you have any further questions, please make sure to reach out and ask me about it. Until next time, have a good day.